Hi everyone. This is a new series that I'll be doing that is separate from the algebraic geometry speedrun, where I'll be learning new types of competition math to get me prepared for the AMO, AME, and AMC next year. So today we'll be starting with a tool known as Muirhead's inequality, which I think is one of the most useful inequalities. Muirhead's inequality is basically the AMGM inequality that is extended so we can easily prove results where one is tasked with proving a certain inequality. So the setup goes like this. Given two sequences of non-negative real numbers, say one is x1, x2, x3, x4, and so on until xn, like this one, and then another one where y1, y2, and so on up to yn is another sequence of non-negative real numbers. For example, x1 to xn, say n equals 3, we could have 5, 1, 0. And also, we'll make sure that the numbers are arranged in descending order like this because it makes it easier to present the theorem or the inequality. And say y1 to yn, or y3 in this case, is 2, 4, 2, 1, 0. So we say that the sequence xn majorizes the sequence yn, as in here this is xn and here this is yn, if each component of xn is greater than each component of yn, not component-wise, but in this way, as I'll present below. Here, we go from 1, x1 should be greater than or equal to y1, and then x2 plus x1 should be greater than or equal to y2 plus y1, and then we continue this string until xn minus 1 plus all the way down to x1 is greater than or equal to yn minus 1 plus ... y1. So if this holds, then we say xn majorizes yn, and we write xn and this inequality looking like a symbol, which means majorizes. So we are given the Muirhead inequality by considering a sequence xn that majorizes a sequence yn, and then different real numbers alpha 1, 2, alpha n, where these are just all non-negative real numbers, such that the inequality holds. The symmetric sum of real alpha 1, x1, alpha 2, x2, and then this product going all the way down to alpha n, xn, is greater than or equal to the symmetric sum of alpha 1, y1, down to alpha n, yn. So, why is this useful? Like, when one sees this, you might think, oh wow, that's a complicated expression. How can I use this in an actual Olympiad problem? Well, if you can recall the symmetric sum, you can realize that this is just a method of extending the AMGM inequality. So let me give you an example by solving this problem below. This problem, we are given three numbers a, b, and c. So these will be our alpha 1 equals a, our alpha 2 equals b, our alpha 3 equals c. And we have that they're greater than 0, so they're non-negative. Well, positive, in fact. And then we're given the fact that a plus b plus c is equal to 1. So let's account for that here. And then we want to show that this inequality holds. Well, I don't like having fractions in the denominator. As you can see in this inequality, let me just copy and paste so that it's easier to see. Since we want to apply this inequality to solve this problem, we note that we don't really want fractions because while you could use the inequality on fractions, it's much easier to use alpha 1, alpha 2, and alpha 3, where alpha 3, these alphas are just in their non-fraction form. So we see that we should probably multiply by ABC to make all of these non-fraction terms, and also this a non-fraction term. So multiplying by ABC, we get ABC over A plus ABC over B plus ABC over C should be greater than or equal to 3 times ABC plus 2 times, and that ABC will just cancel, so it's A cubed plus B cubed plus C cubed, right? But then these just cancel, so we're left with the symmetric polynomial AB plus BC plus AC is less than or equal to 3ABC plus 2A cubed plus B cubed plus C cubed. And this is the final proof, inequality that we want to prove. So this is what we have so far. But then we realize that A plus B plus C is merely 1 by this assumption given here. So we realize multiplying by A plus B plus C will do nothing to the equation. And we want to multiply by A plus B plus C on this left side. A plus B plus C multiplied by AB plus BC plus AC should be less than or equal to 3ABC plus 2A cubed plus B cubed plus C cubed multiplied by 2. The reason for this is, notice that these are all degree 2 polynomials, as in they have, they're 2 degree 1 polynomials, or A and B and C, 2 of these multiplied together. So we can think of these as degree 2. However, on this side, we have degree 3 polynomials, as in they have 3 A or B or C terms. We don't want that because in inequalities, as a rule of thumb, it's usually good to compare terms that have the same degree. We notice that multiplying by A plus B plus C will not affect the inequality, yet it will make all terms have the same degree. So multiplying this out, we get A squared plus B, A squared B plus ABC plus A squared C plus AB squared plus B squared C plus ABC plus ABC again plus BC squared plus AC squared as our final result. So we see that this whole thing should be less than 3ABC plus 2A cubed plus B cubed plus C cubed. Notice that we have 3 ABCs here, which means that we may just cancel these with this 3ABC on the other side. So let's rewrite the inequality in the form that we have now. All of these steps are just used to set up the inequality that we will use later, or the Muirhead inequality. Plus B squared C plus BC squared plus AC squared is less than or equal to 2A cubed plus B cubed C cubed. Now we have everything necessary to use the Muirhead inequality, which I'll bring down here. So we see that these are just symmetric polynomials, and so are these. We'll make the sequence, since we want to do less than or equal to, these a cubed, b cubed, c cubed should define some type of symmetric sum of the alphas raised to the x's. So we want to find a sequence xn where it would give us 2a cubed plus b cubed plus c cubed when taking the symmetric sum. And since there's three terms, a, b, and c, we will have three alphas, a1, alpha 1, alpha 2, alpha 3, and thus we should choose a sequence xn where we have x1, x2, x3. But then a natural choice for that would be 3, 0, 0, because taking the symmetric sum, we get a cubed plus a cubed plus b cubed plus b cubed plus c cubed plus c cubed. Why? Well, notice that if we take a, b, c, the symmetric sum is just the sum of all permutations of these numbers in place of the alphas. So alpha, let's fix a as alpha 1. Then b and c are just going to be can be in the position bc or cb, which is why there's going to be two alphas, two a's, I mean. And similarly, if we fix b as our alpha 1, or the term that has the cubed, we're going to have AC and then CA in the place of zeros. So AC and CA, which is why there's two B's. And by similar reasoning, there's going to be two C's. So we have indeed found the X sequence that gives the right side of the inequality. So it's clear that by the Muirhead inequality, if we were to find a sequence such that that is majorized by 3, 0, 0, corresponding to this symmetric polynomial here, then we will have the result. But then clearly that sequence will be 2, 1, 0. Why? Well, we see that each of the squared terms has 1, and each these are just the symmetric sums where the b and the c's alternate, as in b can take on the value 1 or 0, c can take on the value 1 or 0 in this way, and then a is fixed as 2. And then we take a permutation, meaning that now we fix b as 2, and a can be either 1 or 0, c can be either 1 or 0. So it's clear that 2, 1, 0 will be right. But then we notice that 3, 0, 0 majorizes 2, 1, 0 because, well, obviously 3 is greater than or equal to 2, and then 3 plus 0 is greater than or equal to 2 plus 1, and that's our result. So since 3, 0, 0 majorizes 2, 1, 0, this symmetric sum should be less than this symmetric sum, which is our result. Sorry for the pretty long-winded explanation. This is my first time doing this, but I hope you learned something new. And thank you for watching.